Professor Dave here. Let's talk about non-ideal gases.
He knows a lot about the science stuff. Professor Dave explains.
We've learned all about ideal gases and the laws that govern them, as well as kinetic molecular theory, which explains why these laws are valid. But we must always recall that when operating in this framework, we are making several assumptions that are not totally accurate. These are two of the postulates of kinetic molecular theory. With ideal gases, we assume that the particles are dimensionless points, but in reality, they are not. Atoms and molecules do occupy a measurable volume, even if it's very small. We also assume that they do not interact with each other when they collide, making only totally elastic collisions. Again, this is not true. If gas particles collide, they can participate in some kind of electrostatic interaction, even if only very briefly. We make these assumptions because these two parameters are completely negligible at atmospheric pressure, where we do most of our chemistry. But there are situations where they are no longer negligible, and when that is the case, we can no longer make those assumptions, as we are dealing with a non-ideal gas. An ideal gas must be very sparse, or have a very large volume in comparison to the volume occupied by the gas particles. If this is the case, we can indeed ignore the volume of the particles and treat them as points. But if a gas is compressed until the particles are very close to one another, occupying a reasonable fraction of the total volume, then it becomes less and less feasible to ignore the volume of the particles. This means that if the pressure increases enough, the ideal gas laws do not hold. Also, in addition to having its particles spread far apart, an ideal gas has its particles moving with high velocities, such that if they happen to fly past each other, they have little chance to interact. But if the gas is compressed, and if the temperature is decreased until the particles are moving very slowly, when they pass by one another, there will be much more of a chance for a dispersion interaction or dipole-dipole interaction if they are polar. This means that if the temperature decreases enough, the ideal gas laws again do not hold. So high pressures and low temperatures cause a gas to deviate from ideal gas behavior. Although it is more difficult to describe non-ideal gas behavior in a quantitative way, we can still do so by using the van der Waals equation. This equation is set up just like the ideal gas law, PV equals nRT, but it includes two correction factors. First, we adjust the pressure term with a correction factor associated with the attraction between the particles of a gas. So instead of P, we get the quantity P plus AN squared over V squared. A is a constant that corresponds to the strength of the attraction between gas particles, which depends on their identity, as larger and more polar molecules will exhibit stronger attractions than smaller and less polar ones. And of course, N and V are moles and volume. Then we will adjust the volume term with a correction factor associated with the volume occupied by the gas particles themselves. So instead of V, we get the quantity V minus NB. B is a constant that corresponds to the size of the gas particles, which will also depend on the identity of the gas. And again, N is moles. The right side of the equation will remain unchanged. Each gas will have its own values for the constants A and B, and we will simply look them up in order to do calculations. Let's make sure to note that the van der Waals equation will reduce to the ideal gas law under ideal gas conditions. If the volume is very large and the number of moles is very small, which results in a gas that is very sparse, this would allow for the assumptions associated with ideal gases to be valid, and these correction terms will approach zero, making them negligible. How important is it to use the van der Waals equation when conditions deviate from ideal gas conditions? Well, let's take a sample of gas and perform the same calculation with each equation to see how much they deviate. Let's say we have a 4.25 liter container holding 3.46 moles of carbon dioxide at 229 degrees Celsius. What is the pressure of this sample? First, let's use the ideal gas law. This will be a very easy calculation. We just rearrange the equation to solve for pressure and then plug in all the data, making sure to use a temperature in Kelvin. 33.5 atmospheres is what we will get. Next, let's use the van der Waals equation. This will be slightly trickier, but still not too bad. First, let's rearrange the equation to solve for pressure by first dividing both sides by V minus NB, and then subtracting the n squared A over V squared term. We will also need to know the values for the constants A and B that are specific to carbon dioxide, which happen to be as follows. Now, given the data we already have, as well as these two constants, we can plug everything in. If we do all the arithmetic, being careful with our order of operations, we will get 32.4 atmospheres. So how do we interpret this result? Well, the 32.4 we got with the van der Waals equation will necessarily be more accurate, and in this case, it looks as though the ideal gas law gave us a pretty reasonable estimate. However, the difference wasn't immense because we are not dealing with an exceptionally high pressure. We could have had a pressure in the hundreds of atmospheres, which would make the deviation more significant. Also, carbon dioxide molecules are nonpolar, so the attractive interactions are not incredibly significant. If we instead used a polar molecule like water, we would see that the ideal gas law would become even less accurate in predicting things about this system. And now we have a firm quantitative understanding of the differences between the ideal gas law and the van der Waals equation, and the different kinds of conditions in which we might want to use one over another. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.